Okay, so good afternoon to all the persons attending this CIDE webinar. It's a great pleasure and honor for me to introduce Giuseppe Cavaliere. Giuseppe needs a little introduction, of course. He's an outstanding econometrician, as we know. He's a professor at the University of Bologna and is affiliated to many distinguished institutions across Europe, such as the University of Copenhagen, Nottingham, and Aarhus, and many more. He's the associate editor of the Journal of Econometrics, the Econometrics Journal, Journal of Time Series Analysis, and he has published widely and very influential papers in many outstanding journals, including the Journal of Econometrics, the Annals of Statistics, Econometric, and many more. So it's a great pleasure for me to welcome Giuseppe and give him the floor.
Thank you very much, Tommaso, for the super kind and way too kind introduction. And actually, it's my pleasure to give a talk in this seminar series. As you know, I've been part and I'm still part of the of CIDE as past president right now, and I will end at the end of this year. So really, it's a big emotion and to be here and to give this talk within this series. So thank you very much for your invitation. Okay, and I will share my slides now. I hope you can see it. Okay, so today I will give a talk on a topic that I've been working on in the last years, which is bootstrap measures with random limit. And just a second, yeah. Okay, so what's the idea? I mean, the bootstrap is, of course, very much applied in practice, and there is a lot of theoretical works dealing with bootstrap validity. And the essential requirement that we want for the bootstrap before applying it is that it is first order valid. So what's the meaning of first order validity? Well, the idea is that you have an estimator with an asymptotic distribution, and you construct a bootstrap algorithm and a bootstrap estimator or statistics such that in the limit, the distribution of the bootstrap statistic conditional on the original data converges in some sense to the asymptotic distribution of the original statistic. So you can implement the bootstrap in order to retrieve critical values of the asymptotic distribution, which could be unknown or could be very complicated and so on. But the issue that sometimes we find is that when you go to the limit and you analyze the asymptotic properties of the bootstrap, you find out that instead of converging to something, to a CDF, the conditional distribution of the bootstrap statistic remains random, even when the sample size gets extremely large. So this is what I call in this talk a random limit bootstrap measure. So the conditional distribution of bootstrap statistic, you go to the limit and it's a random CDF. So what I want to do today is to give you an introduction of the main issues related to random limit bootstrap measures, and to show you that actually, even if the bootstrap in this situation is not valid in the classic sense, it can still be a very useful inferential tool. So these are the main takeaways that from this talk. The first is probably the most important, is that if you don't have classic bootstrap validity, so the bootstrap distribution does not mimic the asymptotic distribution, it doesn't mean that the bootstrap is invalid. Still, the bootstrap can provide reliable inference. Bootstrap validity can indeed be proved in cases where the limit distribution of the bootstrap statistic is random. So we don't need to panic in these situations. We have just to take a different route when we want to analyze whether the bootstrap is useful or not. And one of the main twists that you need to do is to focus on the properties of the bootstrap p-values rather than on the ability of the bootstrap to mimic an asymptotic distribution. So this is an essential step to establish possible bootstrap validity in case the bootstrap measure is random in the limit. And there is an investment that has to be done, and in particular, if you want to analyze validity of the bootstrap when you have these random measures, you need a different machinery, and essentially this is the theory of random measures that one can find in several books and articles by Kallenberg and others. Last thing before starting, I want to stress that this is based on joint works with 4 wonderful co-authors that I've been lucky to meet during the last years, which are Ilyan Georgiev, Rob Taylor, and Anna Srabeck and Peter Boswijk. So my talk will be based on works developed with them during the last several years. Okay, so let me just try to fix the notation now. So the idea, as I said, is that the bootstrap is a device to estimate an asymptotic distribution of a statistic of interest. Think of an estimator or a test statistic or whatever you need. And with y1 to yn, I denote the sample data we have. And then we have our statistic, which is tau n in this slide, which is a function of the data. And I assume that this statistic, which this is usually the case, has an asymptotic distribution, which is denoted as tau infinity. And this means essentially that if I look at the CDF of my original statistic, tau n, this converges to the CDF of the asymptotic distribution. I'm a bit sloppy about the technical, further technical condition that you need, but this is essentially the idea. Okay, so we have a CDF that converges to the CDF of the asymptotic distribution. Okay, now we decide to attack the problem with the bootstrap, and we generate or create a bootstrap sample, which is denoted by y star here. And usually the bootstrap sample is a function of the original data, and also of some bootstrap innovations that we merge with the original data in order to generate the bootstrap samples. So for instance, if you think about the IID bootstrap, this eta 1 star to eta n star could be the number of times we pick up one of the original observations or some residuals which we are resampling. If you do a wild bootstrap, then you take all your residuals and you multiply by some random shocks, and these are indeed these random shocks. And if you do a permutation, these quantities could just be a random permutation of the numbers between 1 to n, and so on. So essentially this covers most uses of the bootstrap. Then we have the bootstrap analog of tau, which we call tau star, which is the bootstrap statistic, which is of course a function of this bootstrap data. Now, the key quantity that we analyze when we do bootstrap inference is this CDF. So this CDF is the conditional distribution of the bootstrap statistic when we condition on the original data. Okay, so in a way, we fix the original data and then we analyze the distribution of the bootstrap statistic conditional on the original data. And usually this conditioning we denote by a little star here. So when I write P star, this is this conditional measure when I'm conditioning on the y's. And the main idea of bootstrap consistency, so this is the leading definition, is that the bootstrap conditional CDF converges as the sample size diverges to the asymptotic distribution that we want to mimic. And of course, this is a stochastic quantity because it is a function of the original data. And so convergence is in some probabilistic sense, usually convergence in probability of convergence almost sure. And this property is called weak convergence in probability, usually denoted by this V star P or just DP or D star P and so on. So with the V star, we are saying essentially that we are looking at the conditional distribution where conditioning is on the data, and then this analysis of distributional convergence is done in probability because the conditional distribution is a random function. Then we need some regularity conditions on this asymptotic CDF, and if, as is often the case, it is continuous, then by Polya's theorem, we find the main result here, which says that the Bootstrap CDF is actually close to the empirical, to the CDF of the original statistic, and the distance between the two vanishes as the sample size diverges. And the key implication is that if you want to use all this machinery to do, say, a test, and we look at the Bootstrap p-values, so the Bootstrap p-values are just the Bootstrap CDF evaluated at the original statistics, so this is the definition. Then, as the sample size diverges, we get convergence to the uniform distribution. This allows us to make inference by controlling, say, the type 1 error probability or the coverage probability of confidence interval. So everything is very straightforward here. But at the end of the day, what we want is this result here, so we can control inference. Now, the interesting or the problematic in some cases situation is that in many cases G star does not converge to the original, to the asymptotic distribution of the original statistic, but even in the limit, it is a random process. And there are many situations. This is just a list of where I found some of these cases. So case of unit roots, and you want to do the Bootstrap when you have unit root processes. Cases of parameters which lie on the boundary of the parameter space. Infinite variance processes, so the variance is not finite. With my co-author Anders, we find out that these random measures appears also when you want to test Bootstrap testing hypothesis on the co-integrating relations in a bar model. Fortunately, this happens only under the alternative and not under the null. Another case is like two-stage least squares when you have weak instruments. This is not clearly documented in the literature, but you get this random limit Bootstrap measures, definitely. In a recent paper in Econometric, Matthias Cattaneo and co-author find that estimators which converge at a slower rate than the usual square root of t experience the same issue. Inference after model selection, when you need to select a model and then you apply the Bootstrap depending on which model you have selected is another case where you can find these random measures. Fixed B asymptotics is another example. Hodges-LeCam superefficient estimators is another one. This was documented by Baran in '97. And recently with Luca Fanelli and Giovanni Angelini, we found that the same issue arises also when you look at Stock and Watson's proxies vars using weak proxies. So it's not an uncommon case. It actually is quite common that the Bootstrap, if it is applied in a particular way, experience this randomness in the limit issue. And of course, if the limit is random, then no way it can coincide with asymptotic distribution, which is by definition a non-random thing. So in all these cases, the Bootstrap is invalid. And let me just explain one of these, some of these. So the first one is this Basava and co-authors papers in the Annals of Statistics 91. They take a random walk. So this is AR1 with a unit root. Epsilon is just IID. And this is notation. I call JC an Ornstein-Uhlenbeck process with the mean reversion parameter C. So we have the standard Brownian motion for C equal to 0. Then I call HC this particular CDF. Okay, so this is, it looks like the Dickey-Fuller distribution, but it's expressed in terms of JC rather than the Brownian motion. And of course, if I put C to 0, this is the CDF of the Dickey-Fuller distribution. Now, we know that if we estimate alpha by OLS and I construct the Dickey-Fuller statistic, then we have convergence to this Dickey-Fuller distribution, which means that the CDF of tau n converges to this function evaluated at, with C set to 0. So this is the usual CDF of the Dickey-Fuller distribution. Now we do the bootstrap, as they suggested in Pasava. So this is the bootstrap DGP, and I replace the unknown alpha with its super consistent OLS estimator, fully parametric bootstrap, so epsilon star is just IID normal. Bootstrap estimator, just OLS of this guy on this guy. Bootstrap test statistic, looks like the Dickey-Fuller, but I'm centering around alpha hat because alpha hat is the true parameter in the bootstrap world. Then we go to the limit, and what Basav and his co-author found is that instead of converging to the Dickey-Fuller, despite the super consistency of this guy, well, it converges to a random CDF. So it converges to H, this function here, evaluated at some random variable tau infinity. And this tau infinity is actually a Dickey-Fuller random variable. So the whole guy is random because this little guy here is random. It's like that the original data in the limit determine this tau infinity, and the bootstrap sample will depend on this tau infinity even in the limit. And this is the randomness that we have. So no way the bootstrap can mimic the Dickey-Fuller distribution. Now, there are way out here, and one approach is just to change the bootstrap algorithm. You can take them out of n bootstrap. I mean, it does very bad in finite sample, but asymptotically it seems to work. And or you can impose the unit root, and that also would work. But if you don't do anything and you just apply a plain vanilla bootstrap, standard bootstrap, you get this randomness of the limit distribution. Andrews 2000 econometrica, he looked at the parameters on the boundary problem. So it takes a very simple location model. Y is equal to theta plus an IID 01 sequence. And the key issue here is that theta is within this bounded parameter space. Okay, so theta cannot take negative values. Now, if you do a Gaussian QMLE, then you estimate theta hat as, you compute theta hat as the maximum between 0 and the sample mean, which makes sense. And you can find out the asymptotic distribution of this quantity. Actually, it's super easy. And the issue is that you get a discontinuity. So if the true theta is in an interior point, then you get convergence to the normal 0,1. But if the true theta is on the boundary, then you get this max between 0 and z. You can think about this as a censored normal 0,1 distribution, censored at 0, for instance. Now, what we would like to have is a bootstrap that mimics both distribution depending on theta. Andrews is looking at, again, at the standard bootstrap. So y star is equal to your estimator plus epsilon stars. Fully parametric bootstrap, IID normal 0,1. Doesn't change if you do a non-parametric bootstrap. QMLE of theta in the bootstrap world is the max between 0 and y bar, so the average of y. This is the bootstrap statistic when you center around theta hat. And now you look at finally at the conditional distribution of your bootstrap statistic. And it's not difficult to find out that you get something that is the CDF of the normal 0,1, but it's multiplied by this indicator function. Okay, so you get a 0 if x is below this value. Otherwise, you get like the normal CDF. The problem is that this quantity is random, and it can be random also in the limit. Now, this doesn't happen if the true theta is an interior point. If it is an interior point, then this quantity diverges to minus infinity, and you get convergence to the normal CDF. Wonderful. But if theta is equal to 0, this quantity no longer diverges, it converges to Z plus here. So at the end of the day, we have the Bootstrap distribution, when we have a parameter on the boundary, converges to this CDF. And this CDF is random because of this random variable here. So again, it's like the Bootstrap distribution depends on the original sample also asymptotically. It matters whether this quantity is 0 or not. And this is why we have the Z plus here. Now, there is another way of writing this convergence, which is written here, is tau star actually converges to the maximum of minus Z plus and Z conditional on Z plus. So it's this conditioning of Z plus that makes the whole thing random. Now, I haven't emphasized this, but you see, instead of the usual convergence in probability that we have, for instance, when we don't have a parameter on the boundary, what we know of this guy is that it's convergence weakly. So we are in a situation where Bootstrap distributions, rather than converging in probability or almost sure to a constant, they converge weakly to a random variable. Now, there are solutions to this problem, but if you don't think about how to implement the Bootstrap in this case, you just get into this mess. Another, actually, this is the start of my work with Ilian and the other co-authors on this random Bootstrap measure thing, is the example of infinite variance. So here we have again a location model. Epsilon t is a symmetric random variable with infinite variance. Then there is this technical condition that epsilon is in the domain of attraction of a stable law with this index. So if you're not familiar about this literature, think about alpha controlling the decaying rate of the tails of the distributions. So you don't have moments of order greater than alpha, essentially. Okay, so here we want to estimate the model. There are, of course, robust ways of doing this, but here just plain OLS. Okay, so suppose that the practitioner doesn't care about the tails and simply do OLS. This is the OLS estimator. This is the standardized statistics. So I take the estimator, subtract the mean, and then I need to standardize by some sequence, which is here. And then in the end, the whole thing will converge to a stable law with a coefficient with index alpha. Now, the key problem here is that I don't know what this guy here is. I don't know alpha. So how can I do inference even in this very simple location model? Yeah, I could try to estimate alpha and then plug in an estimator of alpha inside here, but it's very complicated. And even if I knew alpha, this function an depends also on some slowly varying function, and the whole thing is unfeasible in practice. So the Bootstrap. Well, if I do the Bootstrap, first of all, I don't have to care about this standardization, because when I compute Bootstrap p-values, this standardization vanishes. So that's not an issue. But there are other issues. So this is just IID Bootstrap. So I take the residuals, do IID resampling from the residuals, and construct the Bootstrap statistic, which is here. Bootstrap estimator, center at the Bootstrap true value. And what happened in this case? Again, a random limit. And this was derived by Knight. This is an amazing paper, one of my favorites in the annals. And it takes the Bootstrap CDF, and it finds out that, well, again, it does not converge in probability, converge in distribution to a very messy conditional distribution, which is represented here. And this thing is random because of these random variables that appears after the conditioning sign here. And essentially, these random variables here comes from the order statistics of the original epsilons. So when you deal with these infinite variance processes, the extremes are so large that they don't wash out even when you let n go into infinity. And as a result, they appear in the limit bootstrap measure. So again, a mess. Classic solution, m out of n. You try it in practice, and it's really dreadful in terms of finite sample properties. Okay, this is a recent example. I've been working on this with Ilyan Anders and Peter Boswijk. Again, a location model, just to simplify. Epsilon t is a martingale difference sequence, homoscedastic. And then we have this random sequence sigma t, which is, of course, the conditional heteroscedasticity, the conditional volatility, sorry. And we work under the assumption of non-stationary volatility. This means that it's a random process, it's non-stationary, and the main assumption is that it can be approximated by a catalog function on 0, 1. So this is the main assumption. And in the limit, we assume that this, say, approximant in D0, 1 of the conditional volatility converges weakly to some stochastic process sigma. The idea of doing this is in this paper by Bruce Hansen, 95 econometric, paper which is very nice, but it really did not, for some reason, take off, really. Some cases, well, this is the example that Hansen has in this paper. So volatility is a nonlinear function of a random walk. And then when you go to the limit, you get a nonlinear function of a Brownian motion. Another case is the case of a Garch-1-1, where which is nearly integrated. This was Nelson 91 idea. So you make the constant of the volatility equation very small. You make alpha 1 very small. You make beta very close to 1. You go to the limit, you get a diffusion. Okay, so what happens if I do OLS estimation of this guy, of me? So this is the OLS estimator minus the true value, square root of t. And you go to the limit and you find that there is this beautiful distribution which depends on a Brownian motion, which comes from the epsilons, and sigma, which comes from the volatility. And the first thing that one should keep in mind is that this quantity here is just a mixed normal distribution with a mixing variable given by the integrated volatility. So the asymptotic distribution is not Gaussian, it's a mixed Gaussian distribution. Fine, let's do the bootstrap. We do the wild bootstrap as we always do when we have heteroscedasticity. This is the bootstrap sample. So I take my epsilons here, I'm assuming that I can observe them, multiplied by the bootstrap shocks, which are IID normal 0, 1. This is the bootstrap statistic. And then conditionally on the data, because of this assumption of normality, the bootstrap statistic is normal with mean 0 and variance given by the V hat defined here, which you can think about as being the quadratic variation of your original process. Now you go to the limit, so you let n go into infinity, and what you find is that in the limit, the distribution is still Gaussian. It's Gaussian, but we have to think of this V hat as something that converges in distribution, but it's fixed in the bootstrap world. In other words, what we have is that the bootstrap CDF converges to the CDF of a normal 0 V conditional on V. So this conditioning on V stays there when you go to the limit. Another way of writing this convergence is that in the limit you get this, the tau star converges to a normal 0 V conditional on V. Now, there is a big difference between this normal 0 V given V and the mixed normal distribution. They are not the same thing. So the bootstrap is unable to estimate the asymptotic distribution of the original statistic. Okay. Now, this was just a preamble, 30 minutes, a bit long, but I hope you got the idea of what is going on in these particular cases. And as I said in the very beginning, the fact that we have a random linear distribution for the Bootstrap statistic, although it invalidates the classic notion of Bootstrap consistency, it does not invalidate Bootstrap validity, because still we can have tests or confidence set with the correct size or coverage probability. And there is another feature which is quite interesting, is that in many of these cases, when you are able to applying the Bootstrap in the correct way, then the Bootstrap delivers conditional inference rather than unconditional inference. Now, there is a big discussion in statistics about of comparing conditional inference with unconditional inference. Of course, I'm not going to get into that debate, but the fact is that often the Bootstrap, in these cases, deliver conditional inference. And this conditional inference feature often delivers efficiency or power gains. Okay, so now I will try to give you the main idea about Bootstrap validity in a very simple Gaussian regression model, show that even in that simple case we have issues related to this random measure thing, and then I will show you how to discuss Bootstrap validity in this framework. If I have time, but I'm going a bit long, I will discuss a test of parameter constancy in regression models. So, okay, this is a very simple linear model, just one regressor. The epsilons are IID normal 0, 1. The x's are independent of the epsilons. I assume that the sum of square of the x's is positive. I estimate beta by OLS. I get this quantity here. Now, the distribution of this quantity is unknown. Of course, I haven't said anything about the distribution of x, so I don't know the distribution of tau n. However, what do we teach to the students? We say, oh, look, you can look at the conditional distribution. You fix the axis, and then you start the conditional distribution of beta hat. And indeed, if you do this, the magic appears, in the sense that conditional on the axis, the distribution of beta hat is Gaussian. It has a random variance, but once you condition on the original data, you can treat this random variance as fixed. Now, another way of writing down this is to say that the conditional CDF of tau n, where I'm conditioning on the regressors, is just the CDF of a normal 0, 1 evaluated at square root of mn x. You see, this is a random CDF because of this mn, which is a random variable. Okay, now we want to bootstrap. We do a fixed regressor, fixed regressor or fixed design bootstrap. So we fix the axis, plug in our bootstrap, our origin estimator beta hat, generate the epsilon star as IID normal 0, 1, fully parametric bootstrap. Bootstrap statistic estimator, just OLS of the dependent on the original axis. Bootstrap statistic, which is here. And what is the distribution of the bootstrap statistic? Now it's super easy once I condition on the original data. So if I fix the original data, the conditional distribution of tau star is a normal 0 m inverse, of course, given m. Given m means that when you condition on the data, it's like conditioning on this m here. You can treat it as non-random. So we have a conditional normal distribution for the bootstrap statistic. And now there are two important facts. First, that this bootstrap conditional CDF actually corresponds to a CDF that we have seen in the previous slide, this one. So there is overlapping between the conditional distribution of the bootstrap statistic and the conditional distribution of the original statistic conditional on the regressor. These two things matches, and this is an important feature for establishing bootstrap validity. The second important fact is that even in this very simple example, you can experience a random limit bootstrap measure.
There is a question from the audience.
Yes. And
Francesco is asking as to whether you are assuming exogeneity for the axis.
In this example, definitely, yes. Yes, the x is completely independent of the epsilons.
Mm-hmm.
Okay, but of course, you have the same issues also in more reasonable or realistic models.
Okay, thank you very much.
You're welcome. Okay, let's focus a little bit on this equation here, and let's look at two cases. The first is the classic textbook case where we have stationarity and ergodicity of the regressor. In this case, this M sample moment matrix M converges in probability to some non-stochastic matrix, and so by the continuous mapping, G star converges to this CDF, which is non-random. And this means that the Bootstrap statistic in the limit is a normal zero M inverse. Good. This is good because also the original statistic has the same limit distribution. And this implies that the Bootstrap is valid in the usual sense. So the Bootstrap statistic mimics the asymptotic distribution of the original statistic. But what happens if we are in the non-stationary case? In the non-stationary case, suppose, for instance, that xt is a random walk. Then, okay, there is an error in this slide. I apologize for this. But in the non-stationary case, mn converges to a random quantity m and converges weakly. So this should be converges weakly, and m should be actually stochastic. So this is wrongly written as non-stochastic. But the main difference is that in the non-stationary case, you get a stochastic matrix here. And if this quantity is stochastic, when you look at the Bootstrap distribution and you go to the limit, you get a stochastic CDF. So the CDF of a normal evaluated at square root of mx for all x's you want to pick up. And another way of writing this is that tau star, the conditional distribution of tau star, conditional on the data, converges to this particular distribution here, which is a normal zero M inverse conditionally on M. So this is not a mixed normal distribution because I'm conditioning on M. So in a way, the Bootstrap mimics a particular component of a mixed normal distribution. This is extremely important. And this is a random CDF because, of course, a random variable because it depends on M, which is random. So the Bootstrap here doesn't work, doesn't replicate the mixed normal distribution, which is the asymptotic distribution of tau n in this case. Is the Bootstrap doing really bad here? No. And to see this, just focus on the Bootstrap p-value. So let's look at the Bootstrap p-values p stars, which this is the definition. And now if I use the following, the facts that we have seen before, so the fact that G star is given by this random CDF, and the fact that tau n conditionally on the regressor has this particular distribution, implies that the Bootstrap p-value is actually uniform. So the Bootstrap delivers exact inference even if you have a sample size of 1 or 2 or 3. Okay? So the fact that we have randomness of the limit distribution doesn't imply that the Bootstrap is useless. On the other hand, in this particular example, the Bootstrap is exact for any sample size. And the standard notion of Bootstrap consistency, this is the textbook definition, does not hold here. This guy converges to something completely different, to a random object. So from this fact is that even if you are in a world where the Bootstrap measure is random, you can have even exact inference. So why we have this uniformity of the p-value? And the key fact, which will be used later for more general application, is that the Bootstrap is mimicking a particular conditional distribution of the original statistic. Actually, the Bootstrap conditional probability mimics the conditional probability function of tau n given the x. So they are exactly the same thing. And because of this equality, and because this quantity here converges weakly to a random CDF, which you see here, and because this limiting random CDF is continuous, this implies that the Bootstrap p-values will be uniform 0, 1, conditionally on the x. So it's extremely powerful result. Whatever x's you have, you apply the Bootstrap and you get uniformity of the p-values. Okay, so the first thing that we learn from this is, as you already have understood, is that we need to redefine the classic notion of bootstrap consistency, and you should focus on the p-values. So let me skip this slide. It's not important. What is important is this definition that we want to consider. So the idea is to say that bootstrap inference is asymptotically valid unconditionally if the bootstrap p-values converges to a uniform distribution, which is written here. The second notion is a bit more appealing, if you can prove it, is that the bootstrap is asymptotically valid conditionally on some function of the data, xn. Xn can be unobservable, can be anything, just measurable with respect to the original data. Then the bootstrap p-values conditionally on x is uniform. So this is simply the definition of bootstrap validity. You are valid if the bootstrap p-values are uniform 0, 1. You are valid conditionally on some x if the bootstrap p-value is uniform 0, 1 conditionally on x, of course, when you go to the limit. Okay, now how can we assess bootstrap validity? I will just show you some results. This is a theorem in a paper with Ilian, and the idea is the following. This is about proving conditional validity of the bootstrap, and it's very similar to what I just showed you for the linear regression model. So suppose that we are in a situation where the bootstrap CDF, this guy here, and the CDF of the original statistic given some x's converge jointly, weakly to the same random CDF. So these two quantities must converge to the same random CDF. Then, first result, if this CDF is continuous, of course, almost surely because it's random, then indeed these two conditional CDFs are close in the submetric when the sample size diverges. And second result, the bootstrap p-value is uniform conditionally on the axis. So if you want to prove this very strong property of conditional validity of the bootstrap given x, then one way of doing this would be to study the asymptotic behavior of these two CDFs and show that they converge to the same continuous limit. And yeah, one remark, of course, if you are not valid conditionally on x, this does not imply that you cannot find another x where you have conditional validity. So this requires some investigation to know or to guess with respect to what you need to condition when you do this kind of arguments. Now, let me just apply this theorem to the infinite variance case that I have shown you before. So we have seen there that the bootstrap fails in the sense that it doesn't make the asymptotic distribution of the original statistic. Now we consider a wild bootstrap. This we do in the following way. So we take the OLS residuals here and we multiply by a sequence of IID 0, 1 random variables. So this is a plain wild bootstrap. But we need to choose W star to have a Rademacher distribution, which is just a fancy way of saying that W star T can be +1 or -1 with probability ½ each. Okay, and what is the asymptotic behavior of this bootstrap statistic? Well, when you go to the limit, again, we find a random measure. So this bootstrap doesn't solve the issue of having a no-random measure in the limit because we have a random measure. And there are similar results in the literature, in particular a paper by Aue and co-authors in Bernoulli. They were considering a simple, a Q-sum statistic applied to an infinite variance case. They do a permutation bootstrap and they find exactly the same thing, a randomness of the limit bootstrap measure. And what they did was essentially to say, fine, we have a limiting distribution which is random, the bootstrap doesn't work. And what they did not realize was that in their particular example, the bootstrap was exact. Okay, so inference was exact even in samples of one observation. So we need another step. We don't have to surrender once we find this random limit measure. Let's see what happened. And actually, what we found in this particular example is that if we look at a particular conditional distribution of the original statistic, where I'm now conditioning on the absolute values of the epsilons, if we go to the limit, we find a random measure. So also this particular conditional distribution of the original statistic is random in the limit. So why is this bootstrap, this wild bootstrap, better than the IID bootstrap? It's better because the bootstrap mimic exactly this conditional distribution in large samples. You see, they converge to the same quantity. And actually, this convergence can be proven to be joint. So we get this joint convergence to this random CDF. And by the theorem that I have just shown you, you have bootstrap validity conditional on the absolute value of the epsilons. Of course, you need to prove that this distribution is continuous, which may not be trivial, but in Knight's paper, there are suggestions about how to do that. So in this case, the bootstrap delivers valid inference conditional on the absolute value of the epsilons. I need the original epsilons to be symmetric. This is the price to pay. Okay, does it work in finite sample? Okay, the fact that it works asymptotically doesn't say much about the finite sample probability, of course, but let's see. So this is the coverage of confidence sets for mu, constructed using the asymptotic distribution, which is unknown in practice, but here, of course, I knew it. So I took the critical values from the asymptotic distribution. I do the IID bootstrap, and we know that it's not valid, and then the wild bootstrap. Alpha is the tail index, so when alpha is equal to 2, in this particular example, I have Gaussian variables, and you can see that the asymptotic test, this confidence interval works, but also the IID bootstrap confidence interval works. Now I make alpha smaller, so I'm killing moments. I kill the variance first, then I kill the mean, and so on. And you can see that the asymptotic confidence set works, but the IID bootstrap fails. You see the confidence intervals get too short, and the coverage is no longer 95%. Let's look at the wild bootstrap. 95% all the way. So, very simple bootstrap. It has a random measure in the limit, but coverage is 95%, even in very small sample, and even when alpha is very small, which means very wild samples. Okay, now I want to show you that the fact that we have conditional validity actually can imply an efficiency gain. And why? Because when we condition on X in a way, we are reducing the space of all possible outcomes. And this indeed makes the bootstrap distribution, say, less volatile than the original one, and than the asymptotic one. Is it good or bad? Well, again, it depends. We have to know this or analyze this on a case-by-case basis. But for instance, in the infinite variance case, there can be very substantial power gains. One thing we have to keep in mind is that the bootstrap power function, if we do a test, or the length of the bootstrap confidence intervals, even in the limit, are random. Okay, so we don't have a power function which is fixed, but we have a random power function. This is, if we want to call it power, sorry, it's a price to pay. Okay, you get a different original sample, you get a different power function. For some original samples, the bootstrap can be very powerful. For other original samples, the bootstrap can have low power. On average, we expect the power to be high. Okay, and let's see again this infinite variance example here. Now I want to report the ratio between the length of the bootstrap confidence interval to the length of the asymptotic confidence interval. So if I get a number below 1, it means that the Bootstrap is doing better than the asymptotic inference. And I start from below because this is the Gaussian case, and you can see that the median ratio is about 1, and also the first quartile and the third quartile, they all converge to 1. So, I mean, doing Bootstrap, doing asymptotic theory, asymptotic confidence set is the same. But look now what happened when alpha gets smaller. So we are losing moments. This is for alpha equal to 1.5. So we don't have variance. And look at the median interval. The median interval is a half. So if you employ Bootstrap inference in this case, on average, the length of your confidence set will be half of the unfeasible asymptotic confidence interval. And if you go down, I mean, the numbers get even more crazy. Okay, this is 4% in length when alpha is equal to 0.75. This is not a very interesting case, but for instance, for 1.25, we get almost something between 1/4 and 1/3. So it's an amazing power gain doing the Bootstrap in this case. Of course, in a single shot, you can be so unlucky that the Bootstrap confidence set is very large, but on average, and these are average over 50,000 replication, you get wonderful results. Okay, now I want to discuss briefly this last 10 minutes Bootstrap unconditional validity. Okay, so instead of trying to condition on some xn, I'm just interested in the asymptotic distribution of the p-values, and I hope that they are uniform. Now I introduce this property by looking at co-integrating regression. So it's again the usual regression model example, but now I assume clearly that xt is a random walk. Epsilon t is a martingale difference sequence. Also jointly with the innovation driving the x. I assume that these two guys are uncorrelated. So I'm making things a little bit simpler. Estimate beta by OLS. And we know all the limit theorem here, and we have the famous result that says that the asymptotic distribution of tau n is mixed Gaussian. Okay, so we have this mixed Gaussianity where the mixing, say, variance is the integral of a square Brownian motion. So nothing new here. Let's do the Bootstrap then. Fixed regressor, I fix the axis here, plug in beta hat, generate the epsilon as IID normal 0, 1, independent of the data. Bootstrap estimator is beta star hat. Bootstrap statistic, center around beta hat. And again, as in the linear model example that I showed you before, the Bootstrap CDF conditionally on the data is the CDF of a Gaussian random variable with a random variance given by these two quantities here, but when I fix this random variance, okay? So this is conditional on the outcome of Mn and omega hat. But the Bootstrap distribution, conditional on the data, is the distribution of a Gaussian random variable. Now, if you go to the limit, we see that this, say, random variance of the Gaussian distribution is still random in the limit. Okay, so we know that this quantity here converges weakly to this random quantity here. It's random because m is this random variable here. So we don't get rid of the randomness in the limit. This randomness disappears in the stationary case. It doesn't disappear in the unit root case. So we have that the Bootstrap mimics, again, not the mixed Gaussian distribution, but a component of the mixed Gaussian distribution. And because of this, the Bootstrap is not valid in the usual sense. However, there is one important feature here, and essentially, if you compare the two distributions, we see that tau n, the asymptotic distribution of tau n, which is this guy, can be obtained by integrating the random CDF of the Bootstrap over M. So if I integrate this quantity over M, I get the mixed normal distribution. And actually, this is a key property to show Bootstrap unconditional validity. So here you can prove it by direct inspection of the p-values, but in general, when the bootstrap distribution average correspond to the asymptotic distribution of the original statistic, you get bootstrap unconditional validity. And this is represented here in this theorem. So suppose that jointly tau n has an asymptotic distribution, and suppose that the bootstrap conditional CDF converges to a particular conditional version of the asymptotic distribution, so P of tau infinity given some x, then magically, if this G is continuous with probability 1, then the bootstrap is unconditionally valid. This is probably one of the most interesting results. It's not really a very strong requirement here. The proof is complicated because you have to prove that this convergence is joint, but the main idea here is simply that if you average the bootstrap distribution and you get the original asymptotic distribution, you are done. You get uniform p-values. Okay. Now, as I said, bootstrap unconditional validity does not imply conditional validity. Now, suppose that the researcher, for some reason, says, well, I want to be valid conditional on the regressors. So whatever my I1 process outcome is, I want the bootstrap p-values to be uniform. So I'm not fine with unconditional validity. I want to be valid conditionally on X. And this is not implied by the previous assumption. We need stronger assumption. And this is an example of what we have to do here. So I need to assume that epsilon t is not just a standard MDS, so it has zero expectation conditional on the past, but it has to be an MDS also when in the information set I put the future of eta. Etas are the shocks that drive the I1 component. So this is quite a strong requirement, I would say. Well, if we do this, if we make this assumption, of course you have to check it on your data, and good luck for that, then we can establish that indeed the bootstrap CDF and the CDF of tau n given the regressors share the same limit. So for the first theorem that I have shown you, we get validity conditionally on the I1 component X. But without this stronger requirement, we just have unconditional bootstrap validity. Now the big discussion is, are we fine with conditional validity or, sorry, with unconditional validity, or do we need to verify conditional validity? Well, of course, it depends on what we need to do, but this is essentially the difference between the two cases. So in the case in the left, we have an example where we have bootstrap validity conditionally on X. And on the right, we have only unconditional validity. So in this Monte Carlo experiment, I generate different rows on X, and then conditionally on X, I have generated many original data, applied the bootstrap, and so on. So for each X, I'm able to simulate the CDF of the p-values, okay? Remember, we want this CDF to be uniform 0, 1. Now, if we have conditional validity with respect to X, you see all these CDFs are very close to the 45-degree line, which is the CDF of the uniform. And when the sample size increases, they get closer and closer to this 45-degree line. So this is a wonderful case of conditional validity. Whatever X we have, we get the same CDF, almost 45-degree line. Now, on the right, we have the case where we have unconditional validity, but we do not have conditional validity. And here you see that the CDF conditionally on X are all over the place. So if I generate one set of regressor, maybe I get this CDF down here. If I take another one, I get another which is S-shaped. If I take another one, I get one up here. So they are all over the place. If I have two samples with two different random walks, then I get two different CDFs. And then the magic of unconditional validity is that when you average over all possible outcomes of X, you get the 45-degree line. So if you could replicate the history an infinite number of times on average, you would control inference, but only if you could repeat this. Okay, for a single draw, you don't know much. Can be here, and so on. If you have conditional validity, well, you know that whatever X you got, you are on the 45-degree line. So this is essentially the difference between the two. Okay, I don't think I have time to show the application of this to Bootstrap test of parameter constancy. You can have a look at the paper with Ilian. There is this application plus further applications. In essence, what we find out is that this famous test proposed by Hansen in 2000, Journal Econometrics, actually has a random, he has a Bootstrap version with a random limit Bootstrap measure. So you didn't realize it, but that's fine because it's quite difficult to understand that you are in this situation. Then what we found out is that despite of this randomness, the Bootstrap is uniform, is valid unconditionally. But if you want the Bootstrap to be valid conditionally on the X, you need further assumptions that one has to verify. Okay, so let me skip all this. And I just conclude. I mean, this is just a summary of what I have said. So there are many cases out there in statistics, econometrics, and so on, where the Bootstrap measure can be random in the limit. This kills the usual notion of Bootstrap validity, in the sense that no way the Bootstrap can estimate asymptotic distribution of the original statistic. However, it's important not to give up in these cases because the Bootstrap can still be applied. And in particular, is on the one hand a device to obtain p-values which are uniformly distributed, so everything is fine. And on the other hand, the Bootstrap delivers conditional inferences, which is quite important in many applied cases. It requires, the analysis of validity of the Bootstrap requires a lot of non-standard tools like this weak convergence of random measures. I haven't had much time to talk about it, but fortunately, there are theorems based on high-level condition that probably can avoid a deep inspection of this machinery. And right now, I'm working with Luca Fanelli and Giovanni Angelini on proxy vars, where, as I said, there can be this problem of random Bootstrap measures when the proxies are weak. And also, I'm working with Peter Boswijk and Anders and Ilian on the non-stationary volatility case. And we have a solution for that case. And well, I hope that Paolo will accept the paper for the next IceCube conference in Cagliari. And if that is the case, hopefully, if you are interested, you can see the presentation of the solution in Cagliari. This, of course, is a joke, but it's also an invitation for all of you to join the IceCube conference in Cagliari, which will be both online, and if you can make it, it will also be in Cagliari. So I really hope to see most of you, all of you there. Okay, thank you very much. Thanks, Tommaso and Francesco. I think I'm done with the presentation.
Thank you very much, Giuseppe, for a very clear and very entertaining presentation. So one of the conclusions, it seems that unconditional validity doesn't seem to be very important, isn't it? It occurs under very mild regularity conditions and possibly averages out very different situations, very different failures, opposite failures, or so on. So it seems that anyway, conditional validity is what matters, isn't it?
Yes. Well, my personal view completely agrees with yours. I mean, if I apply the Bootstrap to a regression model, I would like to be varied whatever the outcome of the regressor is. But we have been arguing with some other people who were not thinking about it the same way. For some people out there, the important thing is to get the unconditional validity result. And then if you want to prove unconditional validity through a conditioning argument, you can do it. But the final result that you want is unconditional validity. Because, I mean, in a frequentist, I guess, interpretation of inference, you want to control things in the long run, right? By repeating the experiments and so on. But I mean, I agree with you that in most of the cases, I would be much happier if I could have a conditional validity. But it's really depend on your feeling of what is important. And I guess that if you ask to 100 statisticians, they give 100 different answers to these kind of questions. Personally, I completely agree with you. One issue, Tommaso, that maybe is important is that suppose that you don't find validity conditionally on your regressors. Maybe you could find validity conditional on some function of the regressors. Okay, so yeah, there are different layers there, and so in the end, it's a little bit complicated. So probably saying, okay, if I'm fine with unconditional validity, it's all right. But personally, I would be happier to have conditional validity. Like in the stochastic volatility case, I would be happy to have validity whatever the volatility is.
Yes.
Not on average.
Can I add on this? But it goes back a bit to the previous question. But maybe making the regressors exogenous makes the life more difficult. I don't know. If you're thinking conditional, I agree no, but in the unconditional, you probably need to integrate out another term. So yes. I don't know if it's the exogeneity or the function that can help about that.
Well, the fact that in my example there is exogeneity, actually it makes a lot of things much simpler, okay? In general, I don't think that matters really. I'm not sure that exogeneity plays a role in this discussion. Clearly, I mean, when you start looking at Bootstrap inference, the hard stuff is to prove derived asymptotic distribution of the Bootstrap statistic, because first you need to know how to solve the asymptotic problem for the original one, and then you add the machinery to do the asymptotic for the Bootstrap. But when we look at this conditional distribution, in all this analysis, the focus is, for instance, the conditional distribution of the original statistic given X. And that can become really messy, because in a way the Bootstrap world is much easier, much simpler than the original world, because of the mechanism that I use to construct the Bootstrap statistic or the Bootstrap sample. So it's true that it has a random conditional measure, but it's quite simple. But if I want to obtain conditional validity, I need to find out what's the limit of a conditional version of the original statistic. And that could be much more complicated. So I don't know.
Thank you.
My experience of exogeneity in this sense could help the analysis of the original statistic. But I'm not sure how much or how deeply it is involved in this kind of arguments.
Okay, then. And so we thank you again, Giuseppe.
I thank you too for the great.
I'm sure that all the audience will join me in the applause and expressing the thanks for your talk.
Thank you very much, and see you in Cagliari then.
See you in Cagliari.